system with permutation symmetry. And please share your screen. I hope you can do this.
Okay, I hope so. Yep.
Okay, hi, and so it's time is for you.
Okay. So can you see my screen?
Oh, not yet. At the moment, we see, at least I see some black screen. Oh, now I see. Okay. Maybe you can put it into presentation mode. Yes, now it's okay. It's
okay. Very good. Okay.
Super.
Yeah. Well, thank you very much. Well, let me first by thanking the organizers for this very kind invitation to participate on this workshop. So I will present some work that we have been doing together. I mean, for a while already. We started with Christina Krauss and Maciej Lewenstein writing a paper, and I'll talk about that, what it's about. And we continue in the last months with Jiΐr Guth and Lorenzo Piroli. And so we have applied this formalism which we developed before. Okay, so let me go directly to the kind of problems that we are interested in. So we have a set of fermionic modes, and they are interacting with each other. So there's everybody is interacting with everybody. And we are interested in what is the ground state of the corresponding Hamiltonian, and we are interested in the thermodynamic limit when the number of modes goes to infinite. So let me be a little bit more precise. So imagine that we have n sides. So we have something like a lattice, and we have n sides, and we have at each side m fermionic modes. So you want there is an annihilation operator which has an index corresponding to the side and another index corresponding to each of the fermionic mode of that side, so like a spin. And we have a Hamiltonian describing the interactions between these fermionic modes, and these interactions should be few body. So for example, two body interactions between the different modes. And what is important, and I'm going to impose here, is that there is a permutational symmetry. Namely, that everybody is interacting with everybody, every lattice side is interacting with every lattice side with the same strength, in a sense. Or if you want, that if you take two lattice sides and permute them, then the Hamiltonian becomes invariant. And so, for example, so we could consider Hubbard-like models in which we would have like a part of the Hamiltonian could be just something like a chemical potential, which is proportional to the number of particles that are at each lattice side. Then it could have some local interactions. So the particles of different spins at one side interact with each other. We could have hopping, so that particles or these fermions actually can hop from one place to another one. And again, so it's everybody to everybody. So from one side, you can hop to all the other sides without changing the spin. You can have also non-local interaction in such a way that if there is a fermion here and there is another fermion here, then there is energy associated to that. So these are the kinds of models that we are interested in the thermodynamic limit. And let me tell you why we are interested in that. So the first thing is because, fermionic problems are very difficult, or many body problems are very difficult. However, if you take permutation of invariant and then you go to the thermodynamic limit, then they become simple. And we know that this is true for spins. And in fact, you have spins in which you have that everybody spins Hamiltonians under permutational symmetry, like the one that I'm considering here. Then you can solve it, the problem exactly, because then mean field theory is exact. Also for spins, I mean, it's not only if you have permutational symmetry, but also you would have a lattice in which you have, now the number of dimensions is not 2, 3, 4, 5, but you take the limit where the number of dimensions is infinite. That's a different problem, but still you have that the mean field theory is exact. And in fact, these two problems turn out for spins to be equivalent. So we want to have something similar for fermions in which we ask the same question. So the first question is, would mean field theory, fermionic mean field theory, be exact in this thermodynamic limit? Or in other words, are Gaussian states enough to describe exactly this problem in the thermodynamic limit? And the other question is does it happen with fermions like with spins, that working in a permutationally invariant problem is equivalent to working in infinite spatial dimensions? So I want to answer these questions here. Then also, I mean, going to infinite dimensions can give you some physical insights. So for example, we know that if we have certain models and we have dimensions that are sufficiently high, spatial dimensions that are sufficiently high, like 3, then many phenomena are related to this infinite limit phenomena And so then what we learn, we solve a phase diagram for the Hubbard model in this permutational invariant system or in an infinite dimensional model, then this can give us some hint of the physics that is going on in the systems. And in particular, it can also tell us about what happens when we have problems in which there are very long range interactions, no? Because they behave like everybody's interacting with everybody. Also, this could give us inspire new variational families. And actually, this is what happens, if you want, with mean field theory. So when you have a problem and you don't know how to solve it, the many of the problem, one possibility is to use mean field with the spins. And then you use it as a variational family of states, and you minimize the energy, and then you can compute then fluctuations and so on. And that's the whole theory that is behind many condensed matter theory problems. And so maybe here we get the family of states, which are non-Gaussian states, a different one, and this can inspire a family of states to do variational calculations now for problems which are not permutational invariant, but they are like the ones that appear in nature. And finally, and I think that that's very much related to this workshop, is also that we want to make a connection between quantum information theory and many-body physics, because the tools that we use in order to solve this kind of problem, or the problem that I'm considering here, is very much inspired by several ideas on quantum information theory. Okay, so that's the outline of the talk. So I start just talking about the method that we use, and it's a method that is based on symmetries and purification. So I will introduce it. It's relatively simple and standard, but anyway, that's what we have been using, developing some ideas. And then I will show you how this method works for the simple case of spins, where we have a permutational invariance, and also we have a lattice in infinite dimensions, and I'll derive how a mean field theory is exact in that limit using the Finetti theorems. These are the tools that are using quantum information theory. And then we will go to the Fermionic problem. That's an interesting one. And then by using the techniques that I told you before and doing something similar with the spins, then we will get the exact result. And then we will see that actually is very different from the spins. So mean field theory is not exact in that limit. It's another set of wave functions, the ones that are exact. And then we have solved the Hubbard model in particular in that limit, and also used this family of state has inspired some variational models in order to study Hubbard model in 2 dimensions. So that's what I want to tell you. And as I mentioned before, so the technique was developed in this first paper from Krause et al. And the applications to Hubbard model is something that we are currently doing. Okay, so let me start with the methods, symmetries, and purification. And so now we have a Hamiltonian, and we can forget now that they're fermions, so that's in general. So we can have spins or fermions. And we have a Hamiltonian, which, as I mentioned before, is permutational invariant. So you can always write it in this form. So you have a Hamiltonian acting on few body, maybe 2 body or 1 body, plus 2 bodies, plus 3 body, few body. And then you permute the spins or the particles that you have, the lattice size that you have, and then you sum with respect to all possible permutations. So the Hamiltonian is a few body Hamiltonian, which is permutational invariant, and that's the way that you can build it. And it has these 2 ingredients. These are the 2 important ingredients: few body interactions and permutationally invariant. Now, of course, the Hamiltonian has this form and is invariant under permutation. So you permute you do any permutation of lattice size, then the Hamiltonian remains invariant, and this is just by construction. That's the Hamiltonian, how it was constructed. I mean, it may have some other symmetries. They could have either abelian symmetries or non-abelian symmetries. So for example, you have spins, it could be still an interaction are SU2 invariant or U1 invariant or so on. And so this can be added, and I will mention later on, because when we study the Hubbard model, then there are some other symmetries, and they can be addressed in the same way with the method that I'm presenting here. And we are interested in the ground state of that Hamiltonian. And as I mentioned, in the thermodynamically, now when the number of sides goes to infinite. And so one has to distinguish 2 cases, and this will be important for later on. The non-degenerate case, so when the ground state of this Hamiltonian is non-degenerate, and the degenerate case, which is when the ground state of this Hamiltonian is degenerate. And something that will be important in what I'm going to say is that actually this symmetry, this permutational symmetry, is non-abelian. So the 2 permutations don't commute, and you will see this will be important for later on. Okay, so let's start with the non-degenerate case. That's the simplest case, in which you have that now the ground state is an eigenstate of the Hamiltonian. It's a unique ground state, so there is no degenerate, and this means that it also has to be an eigenstate of all permutations, right? So if you take the ground state and it's not degenerate and apply permutation, since it commutes with the Hamiltonian, it has to give something which is proportional to the ground state. And since the permutation Hamiltonian has eigenvalues plus or minus 1, it has to be equal to the same or minus the state that you have. And now let's just do a very simple calculation and transform this problem into something that can be reformulated into something more like a quantum information problem, and that can be solved with the Finetti theorem. And for that, what we do is that we write the ground state energy as the minimum with respect to all possible states of the expectation value of the Hamiltonian, where these states have to be normalized. I will not write normalizations and things like that. And so now what we can do is that we can replace this Hamiltonian here, and that's what I did here. I replaced by the sum with the permutations, and now I realize that since I have a ground state that is unique, is not degenerate, then the one that minimizes this quantity will have permutation, will be the ground state, so we'll have the permutational symmetry. So the permutation acting on psi will be equal to plus minus psi, and the sign will cancel with that. So what will happen is that I can get rid of the permutations. And so I have a sum of terms which are all the same. So now this does not depend on the permutation. So this is nothing else than the number of permutations times the minimum of the two particle energy, the few particle energy, taking on a state that has the permutational symmetry. So at the end, finding the ground state for this problem would be just take the states that are permutational invariant, go to the subspace of state permutational invariant, take one of the terms of the Hamiltonian and minimize the energy with respect to all the states that live in that space. And okay, so at the end, you see that it's kind of a few body problem, because I mean, there's a few body Hamiltonian, there are two body Hamiltonian, which we have here. So the difficulty is imposing that this state lives in the symmetric space, that the psi is symmetric. However, we know actually that when n goes to infinite, this space, that this symmetric space, becomes very simple. And because very simple, because it contains basically product states. And so that's what the Finetti theorem tells you. And so now, but before doing that, let me go to the non-degenerate case. So this is the case that we are in, so that would be more interesting later on. So we have, again, the permutations are non-abelian, so they don't commute in general. And so imagine that now the ground state is degenerate. So it happens that there are several ground states, or states that have that energy. So if you apply the permutations, maybe the state is invariant and with respect to some permutations, but it will not be invariant with respect to all permutations. So my permutation may change the space within the degenerate eigenspace. And so if we try to do the same thing as we did before, so yes, write the ground state energy as a minimization problem, then we cannot use the trick that we used before. This p psi acting on psi is not the same. So this will be wrong. So this means that if we try to solve the problem now, as we did it in the degenerate case, we will not find the solution. And in fact, this will be important, because then when we solve the problem, we will find a way of solving the problem. Then we can compare the cases in which we can solve the problem in the symmetric space or not. And whenever we cannot find it in the symmetric space, we mean that there is some degeneracy, and this will give rise to some symmetry breaking. And so it's a way of detecting symmetry breaking or degeneracy. Okay, and so what do we do now in the case of non-degenerate? We cannot use the symmetric space. Well, the idea is to use purifications. And so that is extremely simple. So now again, we have the ground space, which is a subspace, no, with certain states, psi alpha here. And so what we can do is that we can take any state in the ground state and then conjugate with respect to all possible symmetries, like for example, all the permutations. So what we do is that we take the convex combination of the state that you obtain after permuting this state, this particular one of the states. And it's very simple to see that this density operator that we get after doing that, first of all, contains all symmetry. So it would be, in our case, permutational invariant. So the state, the density operator is permutational invariant. And also it has the lowest energy. And the reason is because when we act with the Hamiltonian, this operation, this permutation will go away, and so we will have this state has exactly the same energy as the original state psi alpha, and this psi alpha has the ground state, so it has E0. So this means that, of course, if we have degeneracy, this is independent of whether we have degeneracy or not, is that if we want to find the ground state, we don't have to take a pure state that is permutational invariant, but we have to take a mixed state that is permutational invariant, and then we are ensured that we will get the ground state if we do that. And so in principle, this is what we should do. We should take the minimum with respect of the trace of rho times h, the few body interactions, the one that corresponds only to few nodes, but the rho has to be permutational invariant. And so it turns out that instead of working with density operators which are permutational invariant, is much better, it's much simpler to work with purifications. So some pure states that live on an extended state. So you just take the Hilbert space you started working in, you make a copy, or in other words, for each latticide, you put another ancillary latticide, write a state now that is entangled between your system and your auxiliary systems, like it's here, and it turns out that then this state, this pure state, is if the original one has certain the density operator has certain symmetries, then you can translate the symmetries to this pure state. So basically, what I'm saying is that what you can do is to work actually with pure states, but the price that you have to pay is that you have to extend your Hilbert space, and these pure states will have the permutational symmetry that you were working at the beginning. So this means that at the end, the whole problem can be solved just by computing the minimizing the energy with respect to pure states that have permutational symmetry and maybe some other symmetries that are in the problem. The only thing is that you have to work with purifications. And so what will happen is that if you find the ground state and this purification that you find, the auxiliary state and the state are product state, then it means that there is no symmetry breaking. So this corresponds to the state that we considered before, in which there is no degeneracy. And however, if you have that there is an entanglement between the system and ancilla, that this corresponds to symmetry breaking. So it's very simple now to solve this problem, at least, well, say simple in quotes, because of course still there is a many-body problem, but you just use this purification with the symmetries, and then by looking at the purification and the solution, then you know whether there is symmetry breaking or not, and you also find the energy. Okay, so let me just go to the case of spins, and so how you can do that. And in the case of spins, then I mean you can take just the same as before, so the same problem. So we have certain spins and some lattices, and some Hamiltonians which have like one body terms, two body terms, you could include three body terms, and so on. And the important thing is that they are permutational invariant. And so the first thing that you notice is that this problem has to be rescaled. So you want to take the thermodynamic limit, the limit n going to infinite, then this Hamiltonian with one particle actually scales like the number of particles, is extensive. However, the two body scales like n squared. So this means that in order in the thermodynamic limit to have competition between these two terms, then we have to multiply the first by n. So this is that the Hamiltonians that we have to consider to make sense has to be something like n times h1 plus h2. Otherwise, as I'm saying before, then only h2, the h1 will not play any role in this problem. So that's a Hamiltonian that you can be written now in some terms in two-body. I mean, you can group things and you can write the Hamiltonian in this form. And so now what you can do is what I told you before. Then you have to compute the ground state energy, and let me talk about the energy density. So the energy divided by n squared. That's the one that makes sense in the thermodynamic limit. And for that, you will have to do what I told you before, to find the ground state, to minimize the energy of one of these terms, just one of them, with the condition that this psi here is symmetric and contains a purification. And so now it turns out that this limit can be taken exactly, and that's what the Finetti theorem does. It tells you that actually the way it works is that you say, well, we know that we are in a symmetric space, and the symmetric space is actually, you can find an over-complete basis of product states. So the symmetric space is spanned by product states. So this means that you could write the state as a linear combination of product states. And these product states will be now states of spins in looking at any direction. So this is why it's called phi here, and that's a measure in the states of pure states. And now what you realize is that whenever you compute any expectation values with the state here, then you will have scalar products of two different states, like the one from the bra and the one of the cat, to the power n-1 or n-2. But in the limit when n going to infinite, if two states are different, then the result is 0. So it's only different than 0 if the states are the same. So this actually, I mean, formally, you realize that this is a delta, a Dirac delta. And since this is a Dirac delta, then automatically you get that the minimization, you could have taken just a product state to do the minimization in the limit n going to infinite. And this is exactly what mean field theory tells you, that in order to do minimization, you go to the thermodynamic limit, you just have to consider the two particle problem and solve a two particle problem now with a purified state that is a product state. And if you solve it, then you will recover mean field theory, and that's how this works. Also, it turns out that now you can solve a different problem. It's not that one spin is interacting with everybody, but there is a spin in some certain geometry, and now you take the number of dimensions to infinite, and you can use exactly the same argument that I told you before to find some upper bound, to find some lower bound. And it turns out that in the thermodynamic limit, these two bounds coincide. And this is why mean field theory is also exact in this particular case. Okay, so I'm ready now to go to the case of fermions. That's the interesting one. And so I go back to the original problem we started with. So we have now these fermions with some fermionic sites with several modes in each of these sites. And now everybody's interacting with everybody. And that's the example that I gave you before. We have, for Hamiltonian, that is permutational invariant. And so, for example, you can have Hamiltonians which have like terms that act only on a single side, like this H1. So this corresponds, for example, to have some chemical potential or to have some on-site interaction, like this one here. There are two species of spin up, spin out, that I call here 1 and 2. Then you can have other terms that are now that include two different sides. And actually, it turns out that for fermions you have to be very careful, because there are terms that have in each side an odd number of fermionic operators and terms that can have an even number of fermionic operators, and you have to distinguish among them. So, for example, an odd term would be the one in which there is hopping. So one fermion can hop from here to here, right? And so that's one here is independent of what is the spin, and also making it permutational invariant. This would be the term. This I call odd because there is an odd operator here. There is an operator, a fermionic operator that is odd, and in the other side there is an odd operator. You can also have even operators. So for example, this would be like something like density operator. So then if there is a spin here and a spin here, then you get some interenergies, a term like that, right? That you have the number operator for a site, the number operator for some other site, and then you sum with respect to all possible sites, and then you will have a permutational invariant. So like before, if we want to make sense of this Hamiltonian, the thermodynamic limit, then we have to see what is the scale. So you can look at the norm of these operators, and it turns out that the first one, like in this case, in the case of spins, scales like n. The even, like in this case of spins, it scales like n squared. However, the odd here, even though it contains two sides, now scales like n. It's very easy to see that. Just take one example, and you will see it right away. Yes. And like the example that is here, in fact, I mean, this can be written in this form, and then you can see how it scales. I don't have time to explain that. This means that if we would naively take the Hamiltonian, which would be n times h1, and then h2, we will not scale these operators, then this odd operator will be 0 in the thermodynamic limit, could be neglected. And so we will have something with respects parity in each of the sides, and this reduces to the spin problem. So the fermionic, I mean, everything is even in each side, then the fermions don't play any role. So we are back to the spin case. If we want to get something non-trivial, then we'll have to scale the term. And so we will have to multiply by n the term. And that's what is the interesting problem there. Okay, so now you can continue using the Finetti theorem now for fermions. So you can follow kind of the idea that you use for the spin system. So I mean, the first thing is you get, I mean, some purification of the state for fermions. You have to be a little bit careful, but you can always, take each of your fermionic modes and add an auxiliary system with fermionic modes, this B system, create maximally entangled states between these two modes, on each side, the system and the auxiliary mode, and you multiply by the square root of the density operator, and you can check that this is a purification and it has the symmetries that should have this permutational symmetry. And so what we will have to do is, according to what I told you, to solve this problem is to, if we want interest in the energy density, would be to minimize the Hamiltonian with states of this form, or possible states of this form, which have permutational symmetry, and then divide by n squared to have some intensive quantity scale. Okay. And so now, as in the case of spins, then we have to see whether we, in the limit n going to infinity, we can simplify those states and we can take something that we can deal with. And so for that, so what we have to do is that we have to consider all possible local operators. You take, for example, a mode operator acting on spin down and mode operator acting on spin up. Then the mode operator, which you multiply a spin up and a spin down operators. Then one that have 3 of them, that one have 4. So you build all possible local operators, and then you make the collective operators by summing to all possible sides. And these operators that you define it this way, there would be 2 kinds of operators. Like before, there will be the ones that have even parity and the odd parity, and you have to distinguish among them. And it turns out that now you can, in this symmetric space, you can build in the same way that before we said that for spins, a complete set were product states. So here in the fermions, that you can prove that actually you can build a complete set of states, which now are a combination of these operators that are here, that have the symmetry. So the even appear in exponentials, the one that are odd appear here only to the power 0 to the power 1, because you are to the power 2 that they are 0, and this is why they simplify. Now you write a general state like an integral with a measure with respect of all possible states, and then you use the tricks as before. You show that if you multiply them, then you have few body expectation values, you have delta functions, and blah 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 blah.
Ignacio, you have some 4 minutes to go.
Okay, thank you. I'm almost finished. Yeah. Okay, so then you find what is the state, and this is the form of the mean field states. Let's say the ones that are exact in the thermodynamic limit. So you can see these are like Gaussian states, and they include, now if you have more modes, then there will be also non-Gaussian states. So these are the ones that are exponentials of symmetric operators that are even, times now global operators also, but that are odd to some powers. And so now that's the result. And it turns out that this is very different from what happens in an infinite lattice, in which, in that case, the dynamical mean field theory is exact. And this is a result that is different. So the question that I asked at the beginning, it's for fermions like for spins, that permutational invariant is equivalent to having an infinite dimensions, and the answer is not. Okay, now equipped with this technique, now we can go to models and try to solve these models. So we can take the Hubbard model. And so that's the Hubbard model. Again, the Hubbard model in the permutational invariants. So where every mode is interacting with, every site is interacting with any other site. And then you can apply the method that I told you before, and you can do it in 2 different ways. First, without purification, and then you find the phase diagram. So you fix the chemical potential. For example, in this case, it's 2 - 1, and it's a function of u and t. Then you find 3 phases. And these 3 phases corresponding, one of them is trivial, the vacuum. The other one is a vacuum in which there is some hopping. So that's these global operators acting on the vacuum. And there is another one which is fulfilling. It's also trivial, which is this double occupation. However, if you use the purification, then you will find that actually there is a different phase diagram. And the fact that you find something that is different, it means that there is symmetry breaking. So you can find what is the difference between these two. When you need a purification, it means that there is a symmetry breaking, and you see that there are filling, hopping, and then there are other phases that appear here. You can do the same thing now, adding interactions between different sites, and then you have a much more complex phase diagram where you can also have pairing and some other. It's not, I don't want to talk about the physics of that, but just telling you that it is possible then to solve this problem, this thermodynamic limit, and also can be used now to inspire variational families of states, that what I told you before also as a motivation. So now what you can do is to take now the Hubbard model in 2 dimensions, the standard Hubbard model with repulsive interactions, and you can use some variational family. I don't have time to explain it, but it's basically the one that we were using for this infinite limit, and find the ground state energy. And so you will find that in a 10 times 10 lattice where we did it, then you obtain better energies than Hartree-Fock. And in fact, if you use Hartree-Fock, you use mean field theory for positive interactions, then it was proven by Lieb many years ago that there cannot be pairing. However, if you put this new family of states, then you find that the ground state there is pairing depending on the chemical potential and so on. So you get a little bit of the flavor that was you're expected to have in the Hubbard model. So with that, I'm finished. Okay. So I was telling you about fermions, interacting fermions, and in the limit where you have an infinite number of modes, and where this is an everybody to everybody, so there are interactions that are permutational invariant. And it turns out that this problem can be solved with techniques. I mean, the techniques that we use were the ones related to the Finetti theorems and purifications, which are inspired by quantum information theory, can have an exact result. You can then try to apply it to models like the Hubbard model with permutational symmetry. Then you can find the phase diagram. You can see different phases. They're actually a rich phase diagram, and you can also use it as a variational calculation. So I mean, we use a very naive variational calculation. So we've found some signatures of something which should be there in the Hubbard model. However, of course, there are many variational methods that work much better than that. So there's no doubt. So it's just to show that, I mean, somehow you can get a little bit better than Hartree-Fock at least. And actually, so what we want to do in the future is getting inspired by this, to get some other variational families of states, also to address problems like Hubbard models in 2 dimensions. Maybe to include some other symmetries also in the problem, not only permutational symmetry. Here we have SE2 symmetries, but also have U1 and so on, and to see what happens. Then we'd like to make a connection that's with DMFT. So as I told you, for fermions, the permutational invariant and the infinite dimension is different. So we want to understand why, and maybe try to also solve the infinite dimension with tools coming from quantum information theory in order to learn, like DMFT, what is the, let's say, the variational wave function that would give to that. And so finally, maybe the most interesting one, it's also difficult, but we are also working on that, is what happens now when there is no permutational invariance, but there's still all-to-all interactions in which they are random. And that looks a little bit more like a chemistry where you, expand in modes, and there are long-range interactions, and so this would correspond more to that. And so maybe one can get good families of states also for quantum chemistry. And I think that I'm probably a bit late, but okay. So that's all. Thank you for your attention.
Thank you very much for your very fascinating talk. And now it's time for questions. And I think it's Christian raised his hand, or is it just applause? Or okay, so it's not his hand. So questions, may I open it? It's Gustavo, please ask your question.
Yeah, so this is a very naive question. For a Hamiltonian to be permutationally invariant, you need all sites in the lattice to interact with the same strength, correct?
Yes.
So a Coulomb interaction is non-permutationally invariant.
No.
Thanks.
That's right. So this is just it's an academic model, of course, and it's just not supposed to solve Coulomb interactions. Yes.
You can have classes of subclasses of permutationally invariant interactions, like in the Coulomb decay, if you want. So that's more realistic and not necessarily random.
Yeah. Yes. No. In fact, I mean, this was not supposed to be a realistic model. What we are solving here, the same thing happens when we study. People have studied spins with permutational invariant. This is not a realistic, but then you derive from there that mean field theory is exact, which is from mathematical physics a very interesting result, and also inspires then variational wave functions that people have used in the spins. And we wanted to do something similar for fermions.
So I'll say this and I'll quit, but there is a class of wave functions which are related to symmetry projection, number or spin and things like that, where the wave function is essentially an elementary symmetric polynomial, which is a permutationally invariant object. And mathematicians have studied them for years, so they're very interesting.
Okay, that's good to know. Thank you.
Okay, the next question is Saber.
Thank you so much for this talk. My question about the scaling, when you took the thermodynamic limit, you have to add n for the one particle, then this will allow you to take the limit. Is there any physical justification why maybe there are other terms that contribute to this limit? I mean, did you try finite size scaling to see what is the physical contribution of each term going to the thermodynamic limit instead of scaling it just to make sure the limit is there?
Well, for the case of spins, there is a very clear physical picture. The single body interactions, there are n terms because there are n lattice sides. However, the two body interactions, there are n squared because there are all possible two body interactions. There are n squared terms. So that's why one Hamiltonian of two body interactions is like n squared, and the single body interactions is like n. And that's why you want to have the same strength when n goes to infinity. You have to scale the single body interactions. Now, for the case of fermions, I mean, this is a well-known fact that you have to also scale. And the idea is that you have an odd number of operators, like a hopping term. And then it turns out that you put, if you take symmetric states, still this creates a mode, like the sum of all possible annihilation operators. This gives a mode. But you do the anti-commutation relation of this mode with a dagger, it gives like n, not n squared. So it's a mode that has a strength, actually, which is the square root of n, not n. And that's the scaling. And so that's, I mean, something similar appears when people do DMFT, that in the thermodynamic limit, and in the infinite limit, sorry, that they have to scale in a different way, the different interactions. And it's very much related to that.
Okay, and the last question is from Frank Pastrata.
So Ignacio, so you stress this fact that actually a mean field and infinite dimension lattices, this is not the same, but this is. Do you have an intuition for this? I see that this comes out of your calculations, but I find this very surprising. And do you have a simple physical explanation why these are different?
Yes. So the idea why the infinite dimensions is the same is based on the fact it's kind of monogamy. You have a spin that is interacting now with an infinite number of nearest neighbors, and then it cannot be entangled to all of them at the same time. So this is why then at the end it's taking a product that is okay. Or seen from a different point of view, you have in a lattice you have one spin that is interacting with another set of spins, and these other set of spins are permutational invariant. By imposing rotational symmetries with respect to all possible axes in infinite dimensions, then you see that what you have is a permutational invariant state, and the permutation. So this means that you could use the Finetti theorem on this kind of spins that are talking to your state, and therefore you could take now a product state. Let's say you have a spin interacting with a set of spins, an infinite spins, and those spins are in permutational invariant state. And you can use the Finetti theorem for those spins and then take a product state. And since it's a product state, then the state that you have in the center also has to be a product state. So this is why product state also works in infinite dimension. However, if you do it with fermions, then of course for this permutational invariant around, you cannot take a product state. You will have to take some other state which are this complicated one. And this gives rise to something that is different. So the fact that in the thermodynamic limit, product states are not the states for fermions already tells you that that's something that is different. I think that's the way I understand it, but yeah, but other than that, I don't have any other intuition.
So then we thank again, Ignacio, your talk. And then the next speaker is going to be Lexin Ding from